Okay, so what is this? So for all the people that said it's a sheep, Magritte technically would say it's a picture of a sheep. Someone said a ram. Anybody else? It is the absolute unit. Congratulations. Nobody in Australia got that joke. So by way of a terrible introduction, the name of this talk is Absolute Unit Test. So this talk is about an idea. It's an idea that has, to some degree, consumed me for at least the last year. I'm definitely going to tell you the idea, but first we're going to talk a little bit, do a little bit of lead up to it. I need to give a bit of background, and then we'll talk about the idea itself. So the genius of this idea, and the excuse for that truly terrible pun, starts with testing. Specifically test-driven development. Ooh. Who's a little bit upset at the moment? Who thought it was a brilliant idea to fly this convict all the way from Australia to lecture you about TDD? Who? Okay, simmer down. Show of hands. Who likes TDD? Okay, I'm going to say it's a little bit less than a third. I'll raise my other hand. Who thinks it's a crock of shit? Interesting. Okay, a few people. That's fine. It's fine, because there's a third option. Who's tried to love TDD but has kind of hit some roadblocks? I'm going to say that's everyone who didn't put up their hand in the first two, and I'm probably in that category. I think that TDD is the right way to develop software. Testing something after you've built it is so waterfall. It's just that trying to apply these TDD's ideas, as we were taught, as I think I was taught, always seems to feel like swimming upstream. Just as a quick aside, whose idea was TDD anyway? Was it closet MRA Bob Martin? Was it Martin Fowler? Who thinks it was Kent Beck? Who thinks it was Alan Perlis? No one thinks any of them. Okay. So it turns out that I went to a conference and I saw Kevin Henley speak last year, and he's done a bit of research, and he found in the proceedings of the NATO software conference, the first conference on software in 1968, that Perlis wrote, "A software system can best be designed if the testing is interlaced with the designing, instead of being used after the design." So they were talking about unit testing, or testing concurrently your code, back as early as 1968. And I found references to unit-style testing in the early 1960s for the software that ran on the Minuteman missile. They didn't kind of have the words that we use to describe it today, but they were definitely building software and testing it at the same time. But nevertheless, I hold it as an article of faith that writing tests at the same time as your code is a good thing. This is an axiom to me. Does anyone agree with me? Who thinks you've had to put your hand on your heart? And that's fair. Who disagrees with me? That's okay. That's cool. Now, I don't really have a background in software engineering. I came to this industry via the System Administration School of Hard Knocks. And so I was introduced to TDD through some random RubyConf talk with Bob Martin up there throwing cards and playing drums and things like that. And he makes a convincing argument, and if you'll forgive me for trying to imitate him, he says, "You are not allowed to write any production code until it is to make a failing unit test pass." Strut. And it goes on like that. You're not allowed to write any more of a unit test then it's sufficient to fail. Compilation failure is a sufficient failure. So you write your test up until the point that it doesn't compile because it's missing the function you're trying to call. Then you go and write the function, then you go back. And you're not allowed to write any production code that is any more code than is sufficient to pass one failing unit test. So it's a little bit autocratic, but it does sound very sensible to me. Because when you hear Martin speak of the benefits of never being more than a few minutes away from all your tests passing, and more importantly, never more than a few minutes away from your code being shippable. What's in master, what's in the head of your development branch is always ready to go. It may be lacking some features, something, but it is not broken. There's a lot to be said from undoing any mistake. It's as simple as Control-Z, and you're back to passing green. So again, this is not just one person's idea. Beck talks about red, green refactor. Recently I saw Kent Beck talk about this new idea he has, which is basically write the code, commit it, and if it passes CI, it gets reverted. There are a lot of people who are kind of riffing on this idea. But the fundamental idea is you write a failing test, you make the test pass however you want. Hard code the variable, just copy the paste it from another method, whatever. Just make the test pass, and then you go back and you clean up. But it turns out that if I knew what I wanted to write up front, then writing the failing test was easy. I wrote the Gorilla HTTP package a long, long time ago using this style because I knew very well what a HTTP package would look like. I had examples to follow. I had some opinions about how I wanted to do it differently from others. And so this worked very well. And it meant that every time I implemented a feature, I'd also written the tests. It was absolutely ready to go. This was the canonical definition of done. Like, nothing shits me more than in a stand-up. You're going around the room and someone says, oh, I fixed that bug. I've implemented that feature. I just have to write the tests. And I think that if we write the code and the tests concurrently, you never have to say that. By the time your feature passes that test and you commit it, you've also written all the testing for it. But as I'm sure pretty much everyone who put up their hand and say they have a fraught relationship with TDD, it's not all beer and Skittles. When I didn't know what I wanted to do, when I was doing research by exploring with code in the program space, working in that TDD style was at least twice as expensive. I'd have to write a test, assuming I knew where I was going, and then write the code to fulfill it. If I discovered I was going down the wrong track, I would have to change the test to point in the opposite direction, and then change the code to follow it. And it kind of got worse. Like that's just at the function level. If you need to backtrack a whole API or a whole chain, when you have functions building on functions, each with their own test, the cost of having to change direction or backtrack is enormous. Like it just went up and to the right. I think that's kind of where I think a lot of the frustration with TDD is. But more fundamentally, changing the tests all the time felt like cheating. It kind of goes like this. Like your tests check your code. That's what they do. But who's checking your tests? Who's testing your tests? Like you have one safety net. That's your tests of your code. If you constantly change the tests, like where's your safety net? I mean, it seemed like the best way to get tests passing is just to delete them entirely. I mean, that gets you to green, guaranteed. So constantly rewriting tests is a lot of unnecessary work. There's no argument there. It was cheating. It wasn't really testing. All I was doing was just asserting the current behavior that the code did and locking it in as a test. And if that changed, well, I just changed the test to match it. They're not tests at that point. They're just accessories after the fact. So one day I ran across this amazing presentation by Ian Cooper. It's called TDD, Where Did It All Go Wrong? When I proposed this talk last month, one of the organizers said, oh, I know Ian, he'll come down for the talk. So I'm like, that's wonderful. No pressure. But I strongly recommend that everyone finds the time for this. It contains a lot more great insights than just the two that I'm going to cover tonight. So if there's one thing you take away from this talk, it's watch his. The first takeaway from Ian's talk was that the system under test, the unit, is not the class. Now, God bless him, Ian's a .NET developer. He can be forgiven for saying the C word. But we're Go programmers. We don't use that word. But if you step back and you think more broadly about the system under test, you can ask this question more broadly of any programming language. I mean, what is the unit of code in a C program? Just yell it out. Anyone? Function? Anybody else? The crash is the unit of code. I'm going to go with the first answer, which is a function. Of course, like the smallest atomic unit in a C program is a function. That is probably what you would unit test. So what is the unit of code in a Java program? Just yell it out. Someone said class. Anybody else? Method? Okay. For the people who said method, and especially the person who said class, really watch Ian's talk. You're going to get a lot out of it. That was really his point, that the unit of code in Java is not the class. But this is what we've always been told. This is conventionally how Java, as a classic OO language, is unit tested. One class, one test case, or one class, one test class. So taking this idea a bit more broadly, what is the unit of code in a Go program? Just yell it out. Someone said function. Anybody else? Behavior. Okay. The program, the package. Okay. These are all good answers. So watching Ian's talk, it got me thinking about something I said a few years ago. At the time, I was just super high on Doug McIlroy. And I said, Go packages embody the spirit of the Unix philosophy. I was entranced by this idea of composing just like you compose programs on a shell. And approaching this argument from Cooper's assertion that the unit of code is not the class or the function, certainly in Go, suddenly it all clicked for me. I argue to you that the unit of software in Go is the package. I think we agree on this. So the second takeaway from Ian's talk is that your test should test the behavior of your unit, not its implementation. And if we agree that the unit of Go programming is the package, then your test should be at the package level. And as you pointed out, the behavior is probably the package's public API. It is the things that you can observe from outside. If we say that a Go package is the atomic unit, there are no quarks and bosons below it. You can't observe anything below the package. As an observer, and I say as an observer in the physics sense, as a consumer of a package from outside, don't worry about what you, the programmer who's writing that package, can do. Think about the people who are calling it from outside. What are the things that they can observe? And they are the package's public API. The public API declares what I do. It says what the package can do. It does not say how I do it. Now, you might think back to the code that you've written. Does it always follow that rule? Does the API talk about itself as what I can do? Or does it do little bits of how it does it leak into that? A really good example is IOReader. We pass in a buffer. That's a pretty big implementation smell that it does buffery things inside. Maybe it's necessary, but think about the idea of your package's public API only in terms of what it can do, not how it can do it. So if you add new behavior to a public API that you want to guarantee, that is when you should write a test. When you implement that behavior, you fulfill that assertion, implementation, you should assert that you've tested that behavior and test the behavior, not the implementation. Because you need to have tests around the behavior, because otherwise people will depend on observable things that they can see from your package. We have many, many cases where we can't change things in the Go standard library because they were never intended side effects, but we can't change them because now people are depending on them. So the unit is not the function, but classical TDD doctrine states that you should not write a line of production code until you have a failing unit test. And the result is, I think, this has led people, and Ian argues that it's led to you writing you're not allowed to write any function, public, private, helper, whatever, without a test first. So you end up with a lot of tests for the internals of your package, for its implementation. This wasted work discourages refactoring. If you think, crap, every time I touch this, every time I try and refactor this, I'm just going to break some tests which are private internal behavior, but I still have to fix them anyway. I still have to change them in that way that I was concerned that writing tests just to lock in the current result of a function is aiding and abetting a crime rather than an assertion. And so it really discourages you from doing this. So in Go, the unit of code is our package. You only need to test the behavior that can be observed. Code coverage here is your guide. If there are branches that can't be exercised from your public API, if you cannot reach into them as an external observer, and you can't exercise that code, maybe you don't need it. When you refactor, your coverage is going to tell you where you need to add tests. If you refactor and your coverage goes down, that means there is new observable behavior in your code that you don't have tested. And the thing is, someone is going to depend on that behavior. This is a perfect example of Hiram's law. Someone is going to depend on that behavior, even if you didn't ever guarantee it. And so you should guarantee it or prohibit it, because otherwise in 2 years, you're going to get a bug report about a thing that you really didn't want to, a piece of implementation detail that you really didn't want to guarantee in the first place. And perhaps if you have good coverage, try things like the fuzz tester, because coverage in Go is only branch testing. So you can look at other things like testing the edge conditions using fuzz testing, which will make your package more robust. I want to quickly talk about how I applied this to the project that I work on. Fundamentally, Contour is just a translator between Kubernetes objects and gRPC objects that go down to Envoy. When you extract out all the Kubernetes logic into one package and all the gRPC logic in another, you're left with this big kind of chewy nugget of business logic in the middle, and that's where all this translation happens. And what happened is you have functions that take an A and return a B prime. And you have, at higher levels, functions that take a set of A's and return a set of B primes. And at higher levels, you have the message that wraps all those, returning a message of the response of B primes. And if you've ever worked with gRPC, this is fairly verbose, but I had helpers to kind of dry up the code a little bit. But what I've found is in the fixtures, I would have to write out effectively the same data structures over and over again as text fixtures. I couldn't use my helpers because that would kind of be, if I use my helpers to generate the code under test as well as the fixtures, how did I know if I was testing the right thing? And as I went up layer after layer, I just found that I was building bigger and bigger fixtures that were very, very brittle. Any change to the business logic wouldn't just break the translator package, but the one above it that took the set of A's and returned set of B's, and the end-to-end test that took a message containing some A's and expected a message containing some B's. And we weren't even insulated from changes to the gRPC definitions that we got from the Envoy project themselves. Updating of our dependency would cause not only if some of the types had changed, would cause a breakage in the business logic, but also in the test for that business logic, even though we'd made no change ourselves. So in trying to apply these, I saw Ian's talk about a year ago, and I've been trying to apply that logic ever since. The first thing that I realized was that the business logic, which is when you get an A and you decide which path you want to translate it from, is different from the function that takes an A and returns its gRPC type. So we separated the business logic from the actual translation of the actual Kubernetes in and gRPC out. And because that was now in its own package, it was completely oblivious to how that A came, whether it came from Kubernetes or whether it was pushed in by a fixture or whatever. And it turned out that now almost all of the business logic, which had been private, pulled into this other package, became public. So we have basically a bunch of functions which are pure functions that take some A's and return you B's. Now, once we have good coverage on that function, on that package, we can call it from the business logic in both the business logic context and in the test for that business logic. And this was the kicker for me. Because the actual conversion is being pushed out into another package, we have good coverage on that. Why should we not be able to use those helpers in other tests? Like, people use methods from the string package all day in both test and business logic context. There's no reason, if you say the strings package has good coverage, we can use it to make test helpers as well as in our code. We should be able to do the same for our own code. And that also meant that because we're now using these helpers in both the business logic and the test context, the changes to gRPC definitions that would previously had these cascading disastrous effects through the whole code base were now constrained only to this one package, which was concerned with taking Kubernetes things and returning gRPC things. People call this the onion architecture. I've heard it called the onion architecture. Alistair Cockburn calls this the hexagon architecture. People called it ports and adapters. Much to my chagrin, if those who came late last year heard Chris James talk about exactly the same thing that I did here. And you even find these ideas in possibly unexpected places. This is the way that Matt Klein, the Envoy developer, thinks about coverage and thinks about writing tests for features. He sticks assertions in and then writes tests until the assertions stop firing. This is unfortunately how you do code coverage in C++, but it's the same idea. And with a nod to Philip Wardler, these are ideas that have not been invented over and over again. They've been rediscovered. And if you know the reference I'm talking about with Wardler, there's a real power to rediscovering the same thing over again. There is a hint that if you keep rediscovering the same idea over and over again, maybe you're on the right track. Now, before I wrap up, the more that I research and think about programming, as I said, I don't have a computer science background. I'm learning this as a layperson. But I'm learning, to my sadness, that there really aren't any rules. There aren't any hard and fast rules. There are only guidelines. What's the difference? I'd say that's probably what people call experience. This is Gladwell's 10,000-hour rule. And the thing is that 10,000 hours is equal parts observation, watching other people work in that field, and practice, repeating what they've done. So knowing when to experiment and when to keep to the code is really what experience is. So with that said, I won't use words like must and mustn't and should and don't. I'm just going to use the word should, and I'll let you make up your mind. You should write tests. I don't think that's too controversial a statement. You should write tests at the same time that you write your code. Hopefully that's not a controversial statement. I think you should. I think this is the right way to develop software. Whether you write the test before or after, it's not important, but certainly don't do the whole thing and then do some manual testing and some code testing. Do it at the same time. Each Go package is a self-contained unit. The more I've tried to apply these ideas from Ian's talk over the last year, the more I'm convinced about this. your tests should assert the observable behavior. They should not test the implementation. So ideas like use code coverage and delete code that isn't reachable from your public API. If it's not reachable from your public API, you don't need to test it. But the one I want to leave you with is if we step back from testing, because this is bigger than testing, and we say you should design your packages around their behavior. The API for your packages should be concerned with its behavior, not its implementation. If you look at the code you've written and the way that you've structured your program, always ask this question: what does this package do? Never ask the question, how does it do it? So I'll leave you with Ian's talk. If you can find time to watch it, I think you'll get an enormous amount out of it. It's a language agnostic talk. There's nothing more about C# than there is about Go in this talk. It's got some really good ideas. I hope you can find the time to watch it. So thank you very much.
Question? Is that on? Yes.
Hello, Dave. You once told me off on Twitter for suggesting that people could have their test code in a different package, such that you are only testing the external footprint of the API.
Yeah, and I've totally changed my tune on that.
I would like an official apology.
That's right. Matt Ryer, I'm very sorry. I'm sorry I was rude to you on Twitter several times. I hope you can find it in your heart to forgive me. Now, the question of should you use _test packages to force yourself to import your own code? I think that's really a matter of personal preference. I don't see the necessity for the boilerplate, but certainly over the last year or so that I've tried to internalize these ideas, I've realized that if you can't, like that physics sense, if you can't observe how this package operates from outside, it doesn't matter how it works. Now, there are some probably nuances to that statement, like that kind of pushes you towards your functions being pure and methods operating on types rather than mucking around with global variables. So it's a little bit aspirational there, but imagine if you felt confident that the only thing that the public API of this package, there is nothing, like it doesn't affect any other state. It doesn't affect. There are no kind of side effects of using this. And if you think about how can I design my package so that is actually true, avoid things like the registration pattern, avoid things like the default muck singleton that kind of silently stuffs things away, then you can actually say my code is more pure, and therefore, if I have good coverage through the public API, there's no need to there is no need to feel like I need to write additional tests inside. Now, I will clarify that statement. There are other cases for writing private tests about complicated business logic, about things when you try to refactor. But the idea that you're not allowed to write a single piece of code anywhere without a failing test for even the smallest helper function, I think is bunk. And I think a lot of that came from the way that TDD was misapplied in the kind of Java and Java kind of era that has been kind of carried forth for a lot.
Any other questions?
Just yell it out. I'll repeat it. Okay, so this is the more general question about mocking. Maybe I should pass this over to Kat, because the ideas behind the onion and the hexagon architecture is that you don't mock. You don't need to, because the data dependencies flow outwards. Is it from this flow inwards? So you never have that situation where you have to mock the database because your package can't work without it. You should pass in, your package should know nothing about the database. So this is a very more nuanced question. I can't really give you a good answer. I'm still trying to figure it out myself, but the more that I try to focus on the behavior, and database is not a behavior. That's an implementation detail. Think about the way that we say accept interfaces, return structs. We never say accept a concrete database. We always try and talk about what is the behavior this database exposes. It lets you read and write things. So you can pass in a read and write thing for others. So maybe that's the answer for mocking, but I don't really have a good answer for that, maybe because I've never really found myself in a situation of having to mock. In Contour, which uses Kubernetes on one end and Envoy on the other, I don't start either of those. I just test the function that Kubernetes would call, and I test the values that we're going to send to Envoy. I never have to have a fake Kubernetes API server just to hairpin a message, a test fixture back to myself. I just call myself directly. I don't really have. I need to do more thinking about that because mocking is a question that comes up a lot. I don't really have a good answer for you. Did you have someone? So the advice was, if you do mock, don't verify the calls to mocks, which very much seems like testing the implementation of your mock, which is really what you don't want to do. Yes, you had your hand up twice.
So your previous answer, were you saying don't do spaghetti dependencies, make packages which are composable?
Yes, your packages should be composable. They should be composable out of the behavior of others, and the way that we do that in Go is through interfaces. So what does that look like? Probably your structs, which define where your main methods are in that type in that package. Probably those fields look more like interfaces than they do like struct types. So you talk about their behavior rather than the actual implementation of a thing from the actual type of a thing from another package. One more question, I think.
Yeah, got a mic here.
I was just saying, isn't that faking? So you take an interface, essentially mocking. I mean, you passing implementation of the database, right? So it's mocking. It's not mocking, but it's mocking because you're faking it has no idea about a SQL database, whatever. But you mocking the behavior.
So maybe it's a question of size. Like, I always try and use the smallest possible interface as a parameter or a struct. Like, don't ask for a read-write closer when you only want to read from a thing. I've never found myself having to have an interface that represents the whole of the database, start transaction, close transaction, because fundamentally, it's a database boils down to write a bunch of keys or read a bunch of keys. That's the behavior. Go and get those keys. I need to. It's strange that in a thing that sits between Kubernetes and Envoy, I just don't seem to find a need to mock. Like, I never need to make a fake Kubernetes or a fake Envoy. And I need to do more research to find out why that just isn't a problem, because I know that mocking is very popular and very problematic. So I need to do more research on that. Paul, last one.
Dave, I'm going to take advantage of holding the mic here and just ask you one final question. Thank you for the awesome talk. You talked about the package being effectively the unit under test. But for those people just starting out, there is always a bit of a challenge as to, well, how should I structure my packages? How should I break down what I'm trying to do into separate packages? And of course, if you get that wrong and you end up testing at the package level, the churn is then at the package level there. What advice would you give to people just sort of starting out?
I would summarize it as this. Like, if we step away from testing and we say, design your packages around their behavior, that's my advice. I I have this kind of meme when I say to people, when people ask, why do you get so upset when people have packages called common or utils or things like that? Because common is not a behavior. Utils is not a behavior. It is absolutely an implementation detail. It's full of implementation crap. So it's kind of example by reduction, or like it's a proof by falsehood. This thing, its name is an implementation. That can't be a good name for a package. What I try and pitch people is, your package's name is a one-word elevator pitch. You don't have 15 seconds with some VC. You have exactly one word, and that is to tell them, and that word is to describe what your package can do for them. If it's server, you've blown it. Serving what? If it's HTTP, you've at least got half a chance. They know at least it doesn't do non-HTTP things. So that I don't have a lot of good advice beyond those two very high-level points, but really, the name of your package should describe what it can do for you. It's very common in Java to have a package for the server types, another package for the client types, and therefore another third package for the common types that are common to both of them. In Go, I think it looks much more like you have a file called server, you have a file called client, maybe have some file called common, or some other transport is from the HTTP package inside the package called HTTP that contains a server, a client, and all the other mechanics it needs behind it. I wish I had more like a 5-step guide for the right way to break down your package, but I think it comes back to the name. You've got to start with the name. The name tells you what it will do for you. Like when you're looking in Godoc, you look for, I need a Mongo driver, or I need a Redis driver, or something like that. You don't search for Redis server. You search for Redis. You certainly don't search for server, because that tells you nothing about what is the thing it's going to serve. So my long-winded answer is, start with the name. All right. The standard library, I hope I don't get into trouble for saying this, is like the Bible. It's written by many people over many times. It contains many contradictory answers. You can find examples in the standard library to support any particular position you want. So do as I say, not as I do. I don't know. Thank you very much.
Thank you, Dave.